Hi guys, okay, today I would like to discuss about the new chapter Transformer Part 1. Okay, for Part 1, we will cover for single phase transformer. So the learning outcome for this topic is, the first one is to explain uh, the principle of ideal single phase transformer. Second one is to calculate the EMF equation for the single phase transformer. The third one is to explain the single phase transformer rating. And the fourth one is to calculate the voltage, current, impedance and the power at the primary and secondary side of the single phase transformer. Okay, so what is transformer? Transformer is a device that transfers electrical energy from one circuit to another through inductively coupled conductor. It can be rise or lower, or we call step up or step down, the voltage in the circuit, but with a corresponding decrease or increase in current. The transformer can be used for many electrical devices and come in a wide variety of size. So figure 1 shows the overall of power system. We have generation, transmission and load. So for the generation to the transmission line, we need a step up transformer to step up the voltage. So for the transmit the power at the transmission line, we need the high voltage so that we can reduce the current. So when we reduce the current, we can reduce the losses at the transmission line. Okay, because the losses equation is P equal to I squared R. So by we reduce the current, then we can reduce the P. Okay. Then for the load side, we need a step down transformer. Okay, so step down transformer, we can step down the voltage based on the requirement of the particular load. Okay, in brief, a transformer is a device that transfers electric power from one circuit to another. Okay, from primary side to the secondary side. And it does so without a change of frequency and without change in form of energy. Okay, the construction has core that could be either using the iron core, air core or ferrite core. Okay, this is the basic construction of the single phase transformer. It consists of the one core and two coil. Okay, the first coil is the first winding connected to the source and the second winding connected to the load. Okay, this is the example of single phase transformer for the very low power application. And this is the single phase, three phase transformer for the high power application. Okay, there are several assumptions for ideal transformer. The first one is neglect the winding resistance of its coil. Second one, neglect its core loss. And the third one is assume all flux is confined to its core, meaning there's no leakage at all. So the efficiency is 100%. Okay, this is the basic principle of the single phase transformer. Okay, we have two winding. The first winding connected to the source and the second winding connected to the load. Okay, when the current is injected at the first winding. Okay, so the flux induced, magnetic field produced increase around this winding. Okay, then this flux will induce the second winding and will induce the voltage at the second winding. Okay, so when current decrease, then the magnetic field will collapse. Okay, for voltage turn current ratio, okay, we can see for the first winding and the second winding, the relationship is here. S1 equal to S2, where S1 is V1 I1 equal to V2 I2. Okay, then we rearrange here. V1 over V2 equal to I2 over I1. Okay, this is the relationship for V1, V2, I2 and I1. And another one is the relationship between N1, N2 and V1, V2. So N1 over N2 equal to V1 over V2. Okay, equal to A. A is the ratio of N1 and N2. Okay, from here, this is the summary. V2 over V1 equal to N2 over N1 equal to I1 over A2 equal to 1 over A. Okay, for turn voltage ratio here also, because the efficiency of the transformer, okay, the ideal transformer is 100%, meaning that the primary power equal to the secondary power. So I1 V1 cos theta equal to I2 V2 cos theta. And also the relationship between V1, V2 and N1 and N2 can we see here. Okay, normally for the single phase transformer rating, okay, is described using voltage and the apparent power, kVA. So this is the rating used, 2400 volt, 120 volt. Okay, meaning that 2400 is for the primary voltage and 120 volt for the secondary voltage, and S is the 48 kVA. So once you know the S and voltage, you can calculate the current for the primary side and the secondary side. Okay, now we will see example 1. This example 1, we have a ideal transformer, okay, that transfer the power from the primary to the secondary. Okay, this is the information given. The voltage is 120 volt, angle 0. The ratio is, the turn ratio is 5. And the impedance load is 4 ohm angle 30 degree, and this is the equation. Load, you have to find the load voltage, okay, the load and the current, load impedance seen from the primary side, the power to the load, and the power output by the generator. Okay, this is the solution for example 1. First one, you have to calculate what is the VL. So VL is EP over A is 24 volt angle 0. And the second one is you have to calculate the primary and secondary current. Okay, so the secondary current is I load equal to VL divided by ZL, 6 angle negative 30 degree. And for the primary current, we have to divide by A. Okay, so we get 1.2 angle negative 30 degree. For impedance seen from the primary side, okay, we can use ZP equal to A squared ZS. Okay, A is the number, the turn ratio. Okay, 5 squared times ZL is 4 ohm angle 30 degree. So the impedance seen from the primary side is 100 ohm angle 30 degree. And another method to get the impedance seen from the primary side is ZP equal to EP divided by IP. Okay, the same result. And for the power, okay, power at the load side is P equal to VI cos theta. Okay, V load I load cos theta, and we get 1 to 4.7 watt. And power output from the generator, so we use EGIG cos theta, and we will get the same power, 1 to 4.7 watt, meaning that the power of the power from the generator equal to the power at the load. Okay, now this is the EMF equation for single phase transformer. Okay, the basic equation is E1 RMS equal to 4.44 N1 FV max, and for E2 is 4.44 and 2 FV max. Okay, how to get this equation, okay, is from this waveform. Okay, this waveform is the sinusoidal waveform for the flux magnet. Okay, then the general equation is phi equal to phi max sine 2 pi ft. Then the instantaneous value of induced EMF per turns is E equal to dv over dt. Okay, then we will get 2 pi f phi cos 2 pi ft. And the maximum EMF induced is 2 pi fv, and the RMS is the maximum divided by 2 or time 0.707. So here we will get 4.44 phi maximum time frequency. N is number of turns, meaning if uh, if we have many turns, so we have to time the number of turns. Okay, so now we will see example 2. Example 2, here 100 kVA, so this is S, and voltage for primary and secondary side, and frequency. And also the given is the secondary turns, is 100 turns. So determine primary and secondary current, number of primary turns, and maximum flux value. Okay, this is the answer or the solution for example 2. For primary power is 100 kVA, okay, divided by V, voltage at the primary, then we will get the primary current. And so for the secondary, S divided by V secondary, and we will get the I secondary. Number of turn for the primary is V1 over V2 times N2 is 2000 turns. And to get the maximum flux value is using this equation, E1 equal to 4.44 N1F flux max, or you can use E2 equal to 4.44 N2F P max. Then you will get the same answer. Okay, next is example 3. Example 3 is one of the partial equation. Okay, you can have a look and try by yourself. Then this is the solution for example 3. Okay, for example 4, okay, so also one of the question from the past final exam. Okay, and this is the solution for example 4. Okay, so this is the exercise 1. Okay, that I want you to try to do it and submit this question. Okay, question 1 and question 2, and submit to the empty assignment. Thank you.